Reduction formulas, what you might have noticed as we've been doing some of these integrals, certainly the ones with powers, and trig is where it happens a lot. And so you might have to integrate, or I don't know, let's say sine to the power of 4. But then when you reduce it down, you then have to reduce sine squared, and so on and so on. And so it allows for some sort of generalisation. So if you make the power n, and then you can come up with a formula to reduce it. So rather than continually integrating, you can apply the formula until you get the integral down to just one easy thing to integrate. That's basically what a reduction formula is. So when it's raised to a power, the vast majority of times we'll use integration by parts to create these formulas. Not always though, because so with those trig ones, basically you just use the same technique you would for the particular trig integral. Now that brings up interesting ones where, because if it was an odd power, we do it one way, and if it was an even power, we do it another way. So you might create two formulas, one for when it's odd, one for when it's even, or something like that. So here's, we're going to find x log x all cubed. Okay. Now I'm going to create a formula to reduce that power down. So I'm going to say, let's make it x log x to the power of n. And so for this one, I'll do it by parts. And so I'd make my u log x to the power of n, in this case, not the x, even though you think, oh, hang on, wouldn't you choose x? Because it'll make it simpler. But if you think about the integration, if I do log x to the power of n, when I integrate, that power is probably going to get bigger because you usually add to the power. And I want to reduce the power. So I'm going to make u log x to the power of n. And so du ends up being n log x to the n minus 1, so the power reduces. V is x, and so v is a half x squared. So I end up with uv minus, n of course is just a constant, so I can bring that out the front, n onto x log, and you'll see now that I've reduced the power in the integral to n minus 1. It's basically the same integral, but the power's different. We just work out the front bit here. It turns out to be e squared on 2 though, and then I'm left with n on 2, but I can now call that I n minus 1. And there's a formula I can now use. So we wanted to find x log x cubed. So that would be I3. And so I3 would be e squared on 2 minus 3 on 2 I2 using the formula. Now I'll use the formula for I2. And I2 would be e squared on 2 minus I1. I1, I can use the formula, e squared on 2 minus half I0. I0, I'll stop there because basically now I've got x dx. Because the log's now to the power of 0, and anything to the power of 0 is 1. And I've got a rather easy integral to go and do. And that is, of course, half x squared, sub in the e, sub in the 1, tidy it up a little bit, and we get our answer. So that's so continually doing that same integration by parts over and over again. Another way I could have done it, I did it using the formula this way. That's sort of breaking it down to get to I0. Some people like to build it up, go the other way. So they start with I0 and say, well, I0 is a half e squared minus 1. And then I1 would be e squared on 2 minus half I0, sub in the I0. Then to get I2, I can sub in what I just found to be I1 and keep building it up. And it's I3 that I want. It's, I guess, just a matter of personal preference, whether you prefer to work your way down to I0 or build it up to the I3. Now, as I say, it's often done by parts, but of course it's not the only one. And the trig ones are often the ones where we don't use it. And here's a classic one, cot to the power of n. Because you remember with the tan ones, which also means for the cot, because they're the complementary ratio, we basically use the same technique every time, regardless of whether the power was odd or even. So I'm going to use that technique. It's just that the power is n now. So integral cot to the n, I'll break the cot to the n up to be cot to the n minus 2 cot squared. change the cot squared into cosec squared minus 1, creating two new integrals that I can split up. And cot to the n minus 2x cosec squared, I can do by a simple substitution. And then over there, I've reduced the power of the cot. So if I did u equals cot x in the first integral, then I get minus u to the n minus 2, add 1 to the power over the power. The second integral becomes I n minus 2, and there's a formula now to work out cotan to the power of something. Reduction formulas often reduce by 2. And that's because of you use a different one for odd and you use a different one for even. So a lot of times you'll find that it'll reduce it by 2 each time. If you don't want to use parts, or you don't think you have to, you could actually try working out what In plus or minus In plus 2 is. Because we know the formula is often reduced by 2, and play around with that, and sometimes magic happens. So here's the cot one. So if I said, okay, well, let's play around with the 2 idea. Let's see what In plus 2 is. Or I could have done In minus 2, it doesn't really matter. It's got to differ by 2. And I get cot to the power of n plus cot to the power of n plus 2, which I'll put into one integral. And that one integral factorises to be cot n to the power of n, outside of 1 plus cot squared, plus 1 plus cot squared is, of course, cosec squared. And now I have a simple integral to do, because I can do the substitution u equals cot x, or you could just notice I have function times derivative. So add 1 to the power over the power, and I get minus cot to the power of n plus 1 over n plus 1. And now I can rearrange it, move the in plus 2, oh sorry, no, don't move the in plus 2, move the in to the other side. Right? Because we want the formula to be in terms of the higher power. Now, you might be thinking, oh, that's no good. We wanted a formula for in, not for the in plus 2. Well, once I've got a formula for in plus 2, I just make n plus 2 equal to n. So the formula becomes that. Because you can sub anything you like in for n. So basically, I'm just taking 2 off everywhere I see n. So the n plus 1 on the bottom of the fraction became n minus 1. The in became in minus 2, and so on and so on. All right, now let's go find it. So I6 becomes minus 1/5 cot to the 5 I4, which then becomes another third cot cubed plus I2. I2 becomes minus cot x minus I0. And I've then got a very simple integral, because cot to the power of 0 is just 1. And so I'm just saying, we'll find the integral of dx, and that is, of course, x. Some other ideas. Integration by parts is great, but by itself sometimes it's not going to work either. And you can see how you're going to use parts along with some sort of algebraic manipulation and maybe a trig identity or two. So here's this one. I'm going to find a formula to integrate 1 plus x squared all to the power of n. They've given me a hint saying it's going to connect in with n minus 1. So in other words, it's saying to me, don't use the idea n and n plus 2 because they're going to differ by 1, not by 2. I suppose I could try n and n minus 1. That could be a way of doing it and just see what happens. But so I've got 1 plus x squared to the power of n dx. So I'm going to let u equal 1 plus x squared to the power of n, because I'm going to do by parts, and I don't want to integrate that bit, because again, that'll raise the power rather than reduce the power. So du becomes 2nx, 1 plus x squared n minus 1. dv is dx, v is x. So I get uv minus integral of v to u. What do I do here? What I'm going to do is change this integral of x squared, 1 plus x squared, into, instead of x squared times it, I'm going to say it's 1 plus x squared minus 1 times it. Okay, so I've just added 1, subtracted 1. But then I'm going to split it into 2 integrals. The first integral, 1 plus x squared times 1 plus x squared to the power of n minus 1. And then the second one is just 1 times 1 plus x squared to the power of n minus 1. But now I can rewrite both integrals in terms of 1 plus x squared to the power of something. Because that middle integral becomes 1 plus x squared all to the power of n. And now I've got my connection, because the middle one will become in, the last one will become in minus 1. All right, but I want in to be the subject, so I'm going to have to move the 2n in to the left-hand side. So I now have 2n plus 1 lots of in, and divide by the 2n plus 1, and I get that lovely formula there. So that one involved algebraic manipulation. Here's one from a very, very long time ago, 1987 HSC. So sometimes they'll actually tell you what the formula is, and that just has the advantage of, oh, well, if I can't create the formula, at least I can show them I know how to use the formula, and I can work out the final integral. They've told us this formula is only going to work when n is greater than or equal to 2, which means when I sub in, I will stop at I is 0. I can't go any further. Okay, so it's 0 to pi on 2 cos to the power of n. Cos to the power of n. How do we deal with cos functions? Well, cos, was that one of the ones that's different depending on whether it's odd and even, wasn't it? Well, we do know I'm going to end up working out an odd one. So could I try that, the technique for odd? Mind you, the formula doesn't actually specify odd or even. No one there says n has to be odd or even. So I've taken out the cos x, which is what we would do if it was an odd power. So I suppose the hint was, well, I'm going to work out cos to an odd power, so I'm going to try the technique I would use for an odd power, and let's just see how that goes. So I've pulled out the factorisation of cos x. Problem is, what I'm left with, I can't guarantee that's an even number, because I don't know whether n is odd or even. And so I can't now go, oh, I can rewrite that as cos squared x to the power of, or do something like that. So I'm going to do it by parts. So u is cos to the n minus 1. Du then becomes this lovely expression, minus n minus 1 cos n minus power of n minus 2 sine x. dv will be cos x, v is sine x. So we get uv minus the integral of v du, but minus minus becomes a plus. I think this first one, the brackets here, the definite part, comes out quite nicely because, of course, cosine of pi on 2 is 0, and sine of 0 is 0, so that whole bracket just is 0. So I'm just left with this integral, n minus 1 cos n minus 2 sine squared. Okay, so there's the substitution, which are going to become 0. The sine squared I'm now going to change to 1 minus cos squared and break it up into two integrals. I now have cos to the power of n minus 2 and cos to the power of n. So I can now rewrite it as I something. So I've got n minus 1 I n minus 2 minus n minus 1 I n. Move the I n's to the left-hand side. And I have n lots of in is n minus 1 I n minus 2, and so I get the required result. Okay, another way I could do it. They've given me the formula. Right? So I'm going to play around with it using the difference of 2 ideas. Now if I use the difference of 2, because you'll notice they've told me it is a difference of 2, as often happens with trig integrals. So I'm going to play around with I n minus 2 minus I n. Okay, so if I substitute in for I n minus 2 and substitute in for I n, I get cos n minus 2 minus cos n, which I can factorise the cos n minus 2, leaves me with 1 minus cos squared, which is, of course, sine squared. So I've got to do it by parts. So I've made the u equal to sine x, not sine squared x. I've made the dv with the sine x, so that I can integrate, because now that is function times derivative, or function to some power times derivative. So uv minus v du, integral of v du. Again, if I substitute into the definite part over here that we've worked out, cos of pi on 2 is 0, sine of 0 is 0. So that it turns out to be 0 is what I'm basically getting at. So I'm left with the 1 on n minus 1 in. n minus 1 I n minus 2 minus n minus 1 I n. Let's make I n the subject, and there we go. We get the formula that's required. Let's now work out cos to the power of 5. Cos to the power of 5 is I5. I5 will be 4/5 I3. I3 will be 2/3 I1. I've got to stop there because I can't go to I negative 1. The formula only works for positive powers here. So that becomes the integral of cos x to the power of 1. We can integrate cos x quite nicely, sin x. And so we just get 8/15 as our answer. Here's one a bit more recent. 2004, question 8b. So this is back in the old days before multiple choice when there were just 8 15-mark questions. I think this was the last question of that paper. Hence, we can expect a high degree of difficulty. So they've defined in to be this integral. So tan to the power of n, 0 to pi and 4. Then they've defined this other expression. Jn is going to be negative 1 to the power of n I 2n. And then you can start at 0 and just as positive integers after that. First thing they've asked us to do, and this I guess is the gift mark of the question, show that in plus 2 is 1 on n plus 1. Because in becomes tan to the power of n, in plus 2, tan to the n plus 2. I can combine that into one integral, factorise the tan to the power of n, leaves me with 1 plus tan squared, which is of course sec squared, and now I have function to the power times the derivative there. Now, if we don't notice, then all right, I'll do a substitution. U equals tan x to u is sec squared. And we've got to change our limits if we do it this way as well, of course. So if I do it with an actual substitution, I get u to the power of n, but the limits are 0 to 1. It is, of course, quicker if you did notice that, and you could have just said, oh, well, that's tan to the power of 1, tan to the power of n, add 1 to the power becomes tan to the n plus 1 over n plus 1. Then you don't have to worry about the limits. Subbing in, and what do you know? We get their answer that they're asking us to find. Here comes the more interesting bit. Deduce then that jn minus 1 ends up being minus 1 to the power of n all over 2n minus 1. All right, well, the definition for jn was minus 1 to the power of n I 2n. So therefore, jn minus 1 to the power of n minus 1 I to the 2n minus 2. Okay. Well, I want to make these minus 1s to the same power because it'll match what I'm trying to show. Now, I've said I've got minus 1 times minus 1 to the n minus 1 is minus 1 to the n, yes. Okay, good. Anyway, so it's minus 1 to the power of n. Factorise that, I get I 2n plus I 2n minus 2. But I'm going to let n equal 2n minus 2. And then I can use that formula. And so the bottom of the fraction becomes 2n minus 2 plus 1, which is 2n minus 1. Okay. Jm is equal to pi on 4 plus the sum of, going from n equals 1 to m, minus 1 to the power of n on 2n minus 1. So Jm, using the formula that we just proved, because logically you would think that is the reason why we just proved part B, so we could go and use it. So I'm making Jm the subject, so I would end up with minus 1 to the power of m, 2m minus 1 plus Jm minus 1. But now I'm going to use the formula again. Jm minus 1 will be minus 1 to the power of m minus 1 on 2m minus 3 plus Jm minus 2. But now I'm going to use the formula again, and again, and again, and again, and again, and again. And eventually I will get to a point where I get to J0. So logically the one before J0, if this is the fraction that ends up before Jm minus 2, then the fraction that comes before J0 must be minus 1 to the power of 1 over 1. Okay? So I have a series, R, sum of. That's what we're trying to prove there. Okay, so there is the series. If you have a look at it, it does satisfy what they want. Minus 1 to the power of n, 2n minus 1, starting at n equals 1, or if n equals 1, I would get 2 minus 1, which is 1 on the bottom of the fraction, and goes to when n is equal to m, and that, sure enough, was my first term here. So I have got that sum part. J0 is simply the integral of dx from 0 to pi and 4, which amazingly turns out to be pi and 4. We have the required result. We're going to use the substitution u equals tan x to show that in is this expression here. So in was the integral from 0 to pi and 4 of tan to the power of n. We're going to use the substitution u equals tan x. Because I can see where I'm heading, I'm going to rewrite this as x equals inverse tan u. Because when I differentiate inverse tan, I get du on 1 plus u squared. You see the connection with what I'm trying to prove? Now I've got to change the limits. So when x equals 0, u equals 0. X equals pi and 4, u equals 1. So subbing it all in, it actually turns out quite nice. Tan to the power of n is just u to the power of n. And the dx is the du on the 1 plus u squared. And so we've got our required result. You could do that without having done part C, without having done part B. But how many people you reckon would have just left that out? Because of the nature of the question, they would have gone, you know. We're going to deduce that in is in between 0 and 1 on n plus 1, and from that conclude that Jn must approach 0 as n approaches infinity. Okay. It is fair enough to say that un on 1 plus u squared is always going to be greater than or equal to 0 for u greater than or equal to 0. Okay? Because the bottom of the fraction is positive, raise a positive to a power, it's going to stay positive, so I can say that. So therefore, the integral from 0 to 1, because I'm just saying for u being greater than or equal to 0, integral from 0 to 1 then, so u is always greater than 0. If I was to imagine that picture, that graph would always be above the axis. So therefore that integral must have a value which is always positive. Or theoretically it could be 0. So that's the first part. I can show in is greater than or equal to 0. That's the easy bit. Now let's have a look at the other bit. Remember a few parts ago we showed in plus 2 is 1 on n plus 1. Okay? Or another way of saying that is in was equal to 1 on n plus 1 minus in plus 2. But we just said in is always greater than or equal to 0. Therefore, in plus 2 must be greater than or equal to 0. Therefore, I'm always taking away something or leaving it, so I can never get anything that's bigger than 1 on n plus 1. So I have the other end of the inequality. That was just the first part of this. Now, we know the limit as n approaches infinity of 1 on n plus 1 would be 0. Okay? So therefore, the limit of in as n approaches infinity is 0. So as n approaches infinity, in will be in between 0 and 0. It must be 0. Okay? But Jn is the limit as n approaches infinity of minus 1 to the power of n of I2n. Well, if in approaches 0, I2n approaches 0 as well. So therefore, the limit as n approaches infinity of Jn is also 0. Right?